Welcome to Space Weather Explorers Week, a set of activities about space weather sponsored by NASA's Carruthers-Corona Observatory. My name is Dr. Brian Mendez. I'm the Planetarium Director at UC Berkeley's Lawrence Hall of Science. Today we're going to be exploring magnetism, and we're going to be exploring magnetism in the world around you, and then making a connection to magnetism that we have globally on the planet Earth, as well as magnetism that we see in the sun and in the interaction between the sun and the Earth, called space weather. To begin the activity, we can just experiment with random materials that you can find around your house and a bar magnet. So if you can find yourself a nice bar magnet that has just two poles, that would be the best kind. You can find these in a variety of different types of stores that sell scientific materials. You can also, of course, get them online. A really cheap source of really strong magnets, bar magnets, is these magnets that are called cow magnets. They look like a big old pill. So I've gathered together a bunch of random bits of material from around the home. And so what you can do is take your bar magnet and play around and see, does the magnet attract or repel any of these materials? And so, for example, it doesn't seem like there's any attraction or repulsion with the rubber. So the rubber erasers, nothing's happening there. Rubber band, same thing. So it doesn't seem like rubber is magnetic. So we can put that aside, not magnetic. The wooden block, nothing's happening there. How about paper clips? Oh, look at that. It's stuck to the paper clip. So we had a magnetic interaction between the paper clip and the magnet. So all of the paper clips, as it turns out, ooh, look at that. You turn one paper clip into a magnet, and then they all stick together. That's fun. Let's try the plastic. Nothing. Plastic straws. Nothing. How about these screw pieces? Ah, they're magnetic. We've got the copper wire. Not magnetic. Okay. How about the string? No magnetism there. How about the aluminum screen? Nope, no magnetism. Paper? No magnetism. We've got different coins from different countries here. All right, those are all not magnetic. Oh, look, the queen was magnetic. And then we've got two nickels here. Not magnetic, which means they don't contain nickel. So if we look at our two different piles of not magnetic and magnetic, what do all of the magnetic things have in common? So that's my first question to you. Most of you are probably saying, well, they're all metal. That is a great observation. They are all metal. However, note there were several pieces of metal that were not magnetic. The aluminum, all of the coins, the copper wire, none of that was magnetic either. So it certainly seems that to be magnetic, you need to be metal, but not all metals are magnetic. And it turns out that there's only three metals that are magnetic. There's iron, there's cobalt, and there's nickel. And in fact, all of these things that we have here are iron. This magnet is made of a mixture of aluminum, cobalt, and nickel, which is a combination of metal. It's called an alloy. Now you just saw how magnets can attract other materials that are so-called magnetic, like iron, nickel, and cobalt. However, magnets can interact with each other in interesting ways as well. They can, of course, attract and stick together. So we've got these two cow magnets that you saw stuck together. However, they can also repel. This end doesn't want to go. That end was trying to push away. This one wanted to attract. And so it turns out magnets have kind of two ends. We call them poles. And opposite poles attract, and like poles repel. So we saw these two poles must be the same. They're pushing away from each other. And then these are opposite, and they attracted each other. And that helps you understand then how compasses work. This compass is a tiny little bar magnet. It has a north and a south end, has different poles, and the ends that are opposite are going to point to each other with this magnet, and the ones that are alike will point away. So you can see that the arrowhead points away right now, and then I flip the magnet over, and now it points toward it. So the compass is just a tiny little magnet that is interacting with the larger magnet. And that's the way you would use a compass if you were, say, out in nature. The Earth itself is a big, giant magnet. And the compass is set up so that when you're out in nature, this little arrowhead will point in a certain direction no matter where you are. And you would take the little letters that are there and you try to line up the N with the arrowhead, and then that way is north, east, south, and west, right? So that's how you would use a compass in nature. We're going to use a compass in this activity to actually map out what the force field of magnetism looks like around a bar magnet. So in order to do that, I'm going to clear away any other magnets from the table. We just want one magnet so we can get a nice clean mapping. And I'm going to use some paper. So we'll take a couple of large sheets of paper. I'm going to tape these up with a little clear plastic tape. And I'm also going to tape them to the table so that it doesn't move on me. Okay, so our paper's in place. Now we'll bring in our bar magnet, and we'll do the same thing. We don't want it to move around either, so we're going to tape it in place. All right, we just want it to stay nice and still. Nothing moves. Great. Okay, and then we'll use one of these clear compasses and a pencil. We'll want to use a pencil rather than a pen because on certain pens, especially ballpoint pens, the little metal ball is made of iron and it can affect our map. So pencil is best here in this case. And all we need to do to get started is to just draw a dot anywhere on the paper. I'm going to put a dot right here. And then we're going to place our compass right on top of the dot, and we'll put another dot where the compass needle points. And then we'll draw a little line that connects those two dots, and we'll draw a little arrow on that line so we know which direction it was pointing. Now I'm going to go back to the original dot, and I'm going to kind of follow the tail. I'm going to keep going like that. And I'm just going to keep picking up the compass and following where it leads, or in this case, following the tail away from that. And every once in a while, as I move here, I can connect those lines, draw in an arrow. You don't need to do it for every single one, but just enough to keep yourself going. So here's where you can get a friend to grab another compass if they want, and they could start a line on the other side of the magnet, and you all can see how quickly you can create this map. And what we're mapping again is kind of the shape of the direction of magnetic forces around the bar magnet. The little compass is basically acting as a test for any magnetic material that might come around. And we can see that as I'm following this tail around, it doesn't make a straight line, it makes a curved line. So the shape of the magnetic force is curved in space, which is fun. Gravity isn't like that. If we were to do this with gravity, we'd just get straight lines pointing toward the center of the Earth. Magnetism gives us these cool shapes for its field of force. And we want to keep doing this until basically either we run off the page or run back into the magnet, which looks like we've done here, right? So we've gone back into the magnet, and I can now trace out the line I've made here, put in a couple of arrows there so that we got that sense of direction. We've done one line of force. So now we can just do this again and again and again until we've kind of filled up our page with tracings of the magnetic field. So I'm going to start another spot over here on the other side. I'm going to pick right here, and we'll see where that leads. I invite you to follow along and start making your own tracing. Okay, so we've completed 2 lines on either side of the magnet, and we can see that the lines converge in these places here, which have been colored on the magnet, blue and red. These are the poles of the magnet. So magnets always come with at least 2 poles, or sometimes in multiples of 2 if the magnet is very, very complicated, but never 1, only multiples of 2. So you always have kind of them in pairs. So I traced out, with 2 lines using the method that we just described here. You saw, of course, when I started that first one, I started very close and it kind of took me right into the magnet. So then I followed the tail backwards to complete the line. And you can see that if I take this compass, I can still move along the line and it still points in the way, which is good. If I hadn't taped it down, things might have shifted and I might be off a little bit. We can take additional compasses and we can come in and we can use them to trace out the field all around the magnet. Move them all around here. And we see that up here, things are either pointing along those lines of the fields we saw, or they're kind of pointing towards the blue pole. And here they're pointing away from the red pole and out. So it's kind of as though the force of magnetism comes out from the red end and then flows back into the blue end. There's this sense of like flow to the magnetic field, out of one pole into the other pole. And so you can see all these little compasses are following along. And so you can see how if we had placed a dot anywhere, we could follow this, right? And we could fill up this page with this lovely pattern of the magnetic field. So Earth has a magnetic field that's much like this. So it has 2 poles, which are kind of roughly aligned with its geographic poles. The sun has an overall shape like this. Several of the planets do. The strongest magnetic fields of planets in our solar system are like in Jupiter and Saturn, much stronger than the Earth's field. And then the strongest magnetic fields are on the sun itself. We see the sun has an overall field that's kind of like this, and then at its surface, it has a bunch of really concentrated fields that also have this kind of dipole look to them. So, for example, we can look at pictures taken in ultraviolet light of the surface of the sun just above the surface in its corona. You can see these loops of magnetism that actually stretch from one sunspot to the other sunspot. The sunspots are like footprints of these magnetic loops. And what you're seeing is the magnetic field actually kind of poking through the surface of the sun, running out and then going back in. And you can see that in the shapes of those loops in the corona of the sun as well. So magnetism is everywhere in nature. It is strongly connected with electricity. And within the sun itself, most of the activity that we see that drives the sunspot cycle is a result of the magnetic field of the sun. If you'd like to learn more, of course, you can do some of the other activities that you'd find at the Space Weather Explorers website, and you can find some of the links to those activities in the description below.